Temperature, temperature, time, temperature, and linear expansion too. Okay, so temperature. What is it? What is temperature? When we talk about temperature, normally people think of it as being hot or cold. That is temperature. But that's not the full story. Really what temperature is it is a measure of how quickly particles are moving. It's really a measure of the average kinetic energy of particles. That is actually what temperature is. It is the average kinetic energy of particles. And while this might seem a little bit weird, it really makes a lot of sense. If a particle is moving faster, it has more kinetic energy. And if a particle has more kinetic energy, then when it bumps into you, it's going to impart more of that kinetic energy into your system. So if you touch a piece of metal that is glowing white hot, the particles in there are moving very, very fast. And when you touch it, that heat energy is going to be transferred to you in a method that we'll talk about in a later video. So if temperature is this average kinetic energy of particles, then we could have a system where one particle is zipping really fast, and one particle is moving slow, and one's 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 moving slow. That doesn't mean that all of them are moving slow, because this one was moving fast. But it means that on average, there is some temperature there. So if we put in something into this box, like a thermometer, this is a poorly drawn thermometer because, you get the idea. This thermometer is actually taking a reading because some of these particles are bumping into the thermometer and then bouncing away. If, on average, the particles that bump into it are moving faster, more energy will be transferred, and that temperature will rise. Okay? That's all that is happening whenever we talk about temperature. It's an average measure of the kinetic energy of particles. It's an average kinetic energy. Okay? So, since these particles are bouncing around, they're moving, they can hit a temperature probe here, a thermometer, and we see some temperature from that. That is the average kinetic energy. Now, because of this, there's also something known as Brownian motion. And it sounds a whole lot cooler than it actually is. Hopefully we're all familiar with the concept of absolute zero. The temperature in which nothing would be moving. A temperature so cold, so to speak, that there isn't actually enough energy for protons and electrons to vibrate within their nucleus or their orbitals. Everything just is frozen, like a perfect Batman villain. Unfortunately, getting down to absolute zero would take an infinite amount of energy to do. And because if you want to take mass and bring it to absolute zero, that mass itself is energy, it's impossible to bring anything down to absolute zero. We can get really close. And actually, the coolest spot in the entire universe is actually here on Earth in laboratories, because we can laser cool things down in very specific ways. But there is always going to be some motion of a particle. And basically, because there's motion, with motion, there is temperature. Which is basically saying that if there's temperature, there's motion. You can read it either way. And simply because of this, we're never able to bring anything down to exactly absolute zero. Even on the smallest scales, we have a little bit of this Brownian motion where something is moving slightly, and because of that, there is some small amount of temperature. It might be insignificant to what we are doing on a bulk scale or a macro scale in this class, but it is still there. So this concept of temperature just being particles moving around is going to play a critical role within this thermodynamics unit. We're going to see it when we talk about ideal gas laws and things like PV-NRT, PV equals nRT. We're going to see it when we talk about expansions as well. So until then, Adios, see you next time, and take it easy.